As we move into Chapter 6, we're moving away from verifying identities and we're moving into talking about inverse circular functions. Now, hopefully you remember the idea of an inverse function from college algebra. A function and its inverse are going to reflect across the line y equals x. So, for example, if I have a graph here and I graph the line with a positive slope of 1, that diagonal line that goes through the origin, that's my line y equals x. If I have a function and its inverse, the original function, let's say the original function looks like, what do I want to do here? Say the original function is an exponential function and it looks like this. Original function is an exponential function. It looks like this. Well, the inverse of that exponential function is going to be a logarithmic function that reflects across that line y equals x. And so it looks like this. These two lines are inverse functions. These two functions are inverse functions. Say this is f of x equals log base 2 of x. And this one is g of x equals 2 to the x power, exponential function and logarithmic function. Those are inverses of each other. Not only do they reflect across that line y equals x, but you can see that their domain and their range switch places. For example, 2 to the first power is 2. So this is the point 1, 2. That becomes the point 2, 1. So literally the domain and range switch places. The x's and the y's switch places. Okay, let's talk about some definitions down here. Recall that for a function f, every element in x in the domain corresponds to one and only one element y in the range. So we can say, let's sketch a graph of a quadratic function. Just my parent quadratic function is that parabola. It's a function, and we know it's a function because each element in the domain corresponds to only one element in the range. When that is true, it passes that vertical line test. Every function is going to pass the vertical line test because each element in the domain corresponds to only one element in the range. What this means is, if a point AB lies on the graph of f, there's no other point on the graph that has A as the first coordinate. Other points may have B as the second coordinate. For example, right there. Let's say this point is 2, 4, and this point is negative 2, 4. This is the only value, the only point on the graph that has 2 as the first coordinate. But 4 is repeated over here. So other points may have B as the second coordinate. However, since the definition of the function allows those range elements to be used more than once, so it's okay. However, if a function is defined so that each range element is used only one time, only once, then we say that we have a one-to-one function. Well, is our parabola, is our quadratic function one-to-one? No, it's not, because we use those range elements more than one time. It is not one-to-one, and we know it's not one-to-one because it fails that horizontal line test. A function is one-to-one if every horizontal line intersects the graph of the function at most one time. So it has to pass, for it to be a one-to-one function, it has to be a function, so it passes the vertical line test, and then it has to be a one-to-one function as well, so it would also have to pass the horizontal line test. Well, we said our parabola, our quadratic function, is not one-to-one. Our cubic function, though, our basic cubic function, f of x equals x cubed, it is one-to-one. It passes both the vertical and the horizontal line test, so it's a good example of a one-to-one function. Now, I can invert anything, but the inverse is only a function if I started with a one-to-one function. So here's my definition of an inverse function. The inverse function of the one-to-one function f is defined as follows. I have the inverse function if y of x such that x of y belongs to f. This is that part where it says the domain and the range switch places. for an inverse function, you exchange the domain and range of the original function. If I were to invert this cubed function, it would be the inverse would be the cube root function. And my cube root function is going to look like this. And I didn't do a great job of sketching the original so that they match, but they're going to reflect across that line y equals x. That's going to be, say, g of x equals cube root of x, the inverse of x cubed. So there's an example of a function and its inverse. Okay, let's look at the next page. It says, do not confuse the -1 in f to the -1 with a negative exponent. That symbol does not represent the reciprocal. It represents the inverse function. And you guys already know this because we have been using our inverse function buttons on our calculator already. If you look at the second function values above your trig function buttons, sine, cosine, and tangent, we have sine inverse, cosine inverse, and tangent inverse. And we've already talked about the fact that that is when you know the function value, but you're looking for the angle. Typically, if we're finding the sine value, we know the angle and we're looking for the function. The angle is our domain. The function value is our range. With an inverse function, I'm going the other way. I know the function value. I need the angle. Okay, let's summarize inverse functions. In a one-to-one function, each x value corresponds to only one y value, and each y value corresponds to only one x value. So each x has a unique y value assigned to it or associated with it. The function f is 1-to-1. If a function f is 1-to-1, then it has an inverse function. Remember, I can invert anything, but that inverse is only a function if what I started with was a 1-to-1 function. The domain of the original function f becomes the range of the inverse function. And the range of the original function f becomes the domain of the inverse function. That is, if the point AB is on the graph of the function, then the point BA is on the graph of the inverse. The graph of the function and its inverse are reflections of each other across that line y equals x. And I could not get this document to change the way I wanted it to, so that was awkward. The graph of the function and its inverse reflect across that line y equals x. We showed you that on the other page of notes. To find an inverse function, from the original, we use the switch and solve method, just like we did in college algebra. Switch and solve. First, you replace f of x with y because they mean the same thing, and then we switch those x and y coordinates, solve for y, and then replace our inverse notation. Now, just a really quick college algebra explanation or example of switch and solve. Let's say we have f of x equals x squared plus 3, and I want to find the inverse of that. I want to find f inverse. Well, my switch and solve method tells me that the very first thing I do is I rewrite it as y equals x squared plus 3. Then I switch my variables. So it's x equals y squared plus 3. And at that point, I solve for y again. If I solve for y again, and I'm going to need this space down here, so I'm going to move over. If I solve for y again, I end up with y squared equals 3 minus x, rearrange terms, y squared equals 3 minus x, and then I take the square root of both sides. When I take the square root of both sides, I get y equals plus or minus the square root of 3 minus x. Now, this was not a 1-to-1 function, so this inverse is not a function. If I had restricted to my domain, however, of the inverse, I would have a range, I would end up with a function that was restricted because it would become the range of that and it would have been restricted. Okay, inverse sine functions. What I was just talking about here, you know what, let me say that again. I started with a quadratic function. Quadratic function is not 1-to-1. So when I invert it, when I turn it on its side, it's no longer a function. If, however, I had restricted this and I said, you know what, I'm not going to look at the entire all real numbers that I can plug in for x. I'm going to restrict that domain in such a way that I only have half of this parabola. Well, when I flip that, it would be a function because I would only have either the plus or the minus of this, not both pieces. That plus or minus is what makes this not a function because it's no longer going to pass my vertical line test. The same is true for our trig functions. When we start with our trig functions, let's think about sine. Our sine function is a wave, right? Our sine function is a wave, and it passes through. We start at the origin and we go up, and that would be one cycle. But the sine is continuous. We have a domain of all real numbers. We have all of these angles through here that we can keep going. So my sine function goes on forever and ever and ever. It is not one-to-one. If I want to invert it, though, I need to restrict it to make it one-to-one so that I'm only looking at one y value. For each of my y values, I only need them to show up once. So here's what we're going to do. We're going to say, you know what? My sine inverse, which I can label two different ways. I can say y equals sine inverse x or y equals arc sine x. Those mean the exact same thing. This means that x equals sine of y for all values negative pi half to positive pi half. So what I have to do is agree, okay, we are going to restrict our function. Instead of looking at the entire function, for our original function, we are only going to consider those values from negative pi half to positive pi half. From negative pi half, I have the lowest possible y value, and then I go through my sine function until I get to positive pi half, which is the largest possible y value. Right here at negative pi half, I have a y value of -1. At positive pi half, I have a y value of +1. I've done the entire range one time, not repeating any of those range values. If I restrict my sine function to only the angles from negative pi half to positive pi half, then I have a one-to-one function. From there to there, that's one-to-one. If I invert it, the inverse is still a function. So we restrict our domain of our original function, which means we have a restricted range on our inverse function. Now, negative pi half to positive pi half, that is the agreed upon values for which we are going to restrict the inverse sine and anything else that depends on that y value. If we look at negative pi half to positive pi half, thinking about the unit circle, we've got quadrants 1, 2, 3, and 4. If I were looking at the graph of that, negative pi half is down here, positive pi half is up here. We're talking about restricting our inverse sine functions to quadrants 4 and 1. Now, we always go in that order, from negative pi half to positive pi half. So if I am going to start with an angle or come up with an angle for a sine function value, it's always going to show up in one of these two. It's going to either be a negative angle in quadrant 4 or a positive angle value in quadrant 1, because that's the agreed upon convention for that restriction. Now, we are not going to be graphing inverse functions. I'm going to show you the graphs of the inverse functions, but we aren't going to be actually graphing them. Okay, we can think of y equals sine inverse x, or y equals arc sine x, same thing, as y is the number, the angle, within that defined interval, that restricted interval, negative pi half to positive pi half inclusive, whose sine function is x. So the domain of y equals sine inverse x is -1 to +1. That's the range of the original sine function. It's the domain of the inverse. I'm plugging in the sine function value. Those are all my possible values. The range of the sine inverse is that restricted domain of the original function from negative pi half to positive pi half, inclusive. Okay, so let's think about this. Find y in each equation. Y is arcsine or sine inverse of square root 3 over 2. Well, what we're saying is y is the angle whose sine function value is square root 3 over 2. Well, if I look at my unit circle, Well, if I look at my unit circle, I know that I have a sine function value of positive square root 3 over 2 in quadrant 1 and quadrant 2. But we are starting with an inverse function. My inverse function is restricted to quadrants 4 and quadrant 1. Sine is negative in quadrant 4, so I have to be talking about the angle in quadrant 1 whose sine function value is square root 3 over 2. Well, the angle in quadrant 1 whose sine function value is square root 3 over 2 is pi third, or 60 degrees. Now let's look at our problem. It does not give us an indication of whether or not it wants degrees or radians, so we're going to give it both. 60 degrees, which is the same thing as pi third radians. That's the angle whose sine function value is square root 3 over 2. Again, because we're starting with an inverse, we only have one angle primarily that is returned because of that restriction. Okay, let's look at B. Y equals sine inverse of negative 1/2. Well, because my sine function value is negative, I know I'm in quadrant 4 because sine inverse is restricted to only quadrants 4 and 1. Quadrant 1 sine is positive, quadrant 4 sine is negative. Negative 1/2 is for the angle 330 degrees, or 11 pi sixth. Except that, remember, we think about it as being negative pi half to positive pi half, or negative 90 to positive 90, not 270 degrees. So what is that reference angle here? That reference angle here is 30, negative 30 degrees, or negative pi sixth. So that's what it returns to me if I were to use my calculator. It would be negative 30 degrees, or negative pi sixth. Here I have a sine function value of a positive square root 2. Well, square root 2 is not within that domain from negative 1 to 1. Square root 2 is greater than 1, so that does not exist. If you were to plug that into your calculator, it would say it's a domain error. Do you see any of these three that's going to give you a domain error as well, that it does not exist? Sine function value cannot be negative 2, so that does not exist. It can, however, be negative 1. Sine function value is negative 1 at negative pi half, which is the same thing as negative 90 degrees. And finally, we've got an arcsine of 1/2. Arcsine is the same thing as sine inverse. It's positive, so we are in quadrant 1. If you look at your unit circle, the angle in quadrant 1 with a positive sine function value of 1/2 is 30 degrees, or pi sixth, depending on if you want degrees or radians. Be sure if you want degrees that you show your degree symbol. If not, it's radians. And 30 radians is not the same thing as 30 degrees. Okay, be certain that the number given for an inverse function value is in the range of that particular inverse function that is being considered. Be sure. Now, remember, you will not be asked to graph. You will not be asked to graph these inverse functions, but we are going to look at the chart for the inverse functions and get all of our information in one location. When we're talking about inverse sine, our domain is the range of the original sine function, so that's negative 1 to 1. The range is restricted, and we have chosen to restrict the range from negative pi half to positive pi half, quadrant 4 and quadrant 1. These are the primary values that we would graph to get our graph. And you can see that sine inverse is an increasing function, and it's continuous on the domain from negative 1 to 1. The x-intercept is at 0, 0, just like my sine function. So the y-intercept's the same place because that's the origin. The graph is symmetric with respect to the origin, so sine inverse is an odd function just like sine is an odd function. For all x in the domain, sine inverse of negative x is the opposite of sine inverse x. Because it's an odd function, I get the opposite of the original function value when I plug in that negative x. All right, let's look at the next page. Inverse cosine. Now, inverse cosine is going to have a restriction as well, but it is restricted not over quadrants 1 and 4. Let's think about this. When I restrict its inverse sine to quadrants 1 and 4, that gave me all of my positive sine function values and all of my negative sine function values. What if I did the same restriction for cosine inverse? Well, cosine is positive in quadrants 1 and 4. So that doesn't help me. That just gives me my positive cofunction values. So I need two continuous quadrants where I have cosine positive and negative. The best way to do that is to restrict cosine inverse to quadrant 1 and 2 from 0 to pi, or 0 to 180 degrees. That gives me all my positive cosine function values and all my negative cosine function values. So anything that is cosine dependent is going to be restricted to quadrants 1 and 2. Anything that is sine or y dependent is going to be restricted to quadrants 4 and 1. Okay, back to our notes. Cosine inverse, or arc cosine, mean the same thing, is restricted y values from 0 to pi. So y is the number, the angle, in the interval from 0 to pi whose cosine value is x. X is the domain, the cosine function value is the domain of the inverse, and that, just like sine, those cosine function values are limited from -1 to +1 inclusive. And then remember, we chose to restrict the range of cosine inverse to those values from 0 to pi because those are two continuous quadrants that include all of my positive and negative cosine function values. Let's look at our unit circle to answer these questions. If I look at these four values, are any of these values outside my domain, or are they all within -1 to 1? All four of these are legitimate cosine function values, so they all exist. All right, arc cosine, or cosine inverse, is 0. Well, in quadrants 1 and 2, where's my cosine function 0? Right here at pi half, or 90 degrees. Where's my cosine function value of +1/2? Well, cosine inverse is positive, and cosine function values are positive in quadrant 1. They're +1/2 at pi third, or 60 degrees. What about a cosine function value of +1? Well, that happens at 0 degrees 0 radians. Cosine function value a negative √2/2. Well, cosine is negative in quadrant 2. It's also negative down here in quadrant 3, but remember we have restrictions. Cosine is a negative √2/2 at the 45 over here at 135 degrees 3 pi 4th radians. 3 pi 4th radians, which is the same thing as 135 degrees. All right, let's fill in our chart about inverse cosine functions. Again, we're not going to be graphing these, but you do need to understand what it means with those restrictions. Domain of the cosine inverse was the range of cosine. So -1 to 1 are those values for the domain of the inverse. The range is what we restricted the domain of the original function to. Because it's cosine, it's based on that x coordinate. It's restricted from 0 to pi because that gets me all of my positive and negative cosine inverse function values. Cosine inverse, as you can see from my graph, is a decreasing function and continuous on its domain, -1 to 1. It does not go through the origin. Its x-intercept is at 1, 0, and its y-intercept is at 0, pi half. You don't need to worry about memorizing those. Again, we're not going to be graphing these functions. This graph is not symmetric with respect to either the y-axis or the origin. So while cosine was an even function, cosine inverse is not either. It doesn't have predictable symmetry for us. All right, let's talk about inverse tangent. Inverse tangent. Now, remember my tangent function value. If I look at tangent theta, that is y over x. I've got y in my denominator, so we are going to consider it as y dependent. That's kind of a Campbellism. I don't know that you'll hear that from another instructor. But remember, sine of theta is y over r, and we restricted sine to -pi half, +pi half. Well, tangent theta is y over x. I'm going to say y dominant, so it has those same restrictions as inverse sine. Tangent inverse, or arctangent x, has restrictions in quadrant 4 and 1 from -pi half to +pi half, just like sine inverse. quadrant 4 and 1. So if I have a negative tangent function value, I'm going to give you a negative angle in quadrant 4. And if I have a positive tangent function value, I'm going to give you a positive angle in quadrant 1. We can think of tangent inverse or arctangent as y is the angle, the number, in that interval negative pi half to positive pi half whose tangent value is x. Now think about tangent function values. Tangent compares the y to the x. It can be anything. That tangent function value is all real numbers. That range, though, is that restricted. Now notice that my restrictions do not include negative pi half and positive pi half. They do not include those endpoints. Because when I look at the graph of my tangent function, it kind of looks like my cube root function. It approaches asymptotes because my original tangent function graph has vertical asymptotes. When I lay it over, it has horizontal asymptotes, so it never gets to those values. It approaches them but never gets there. My domain is all real numbers. The range is not inclusive, negative pi half to positive pi half. Those are where my asymptotes fall. Inverse tangent is increasing and continuous on its domain, all real numbers. The x-intercept is at the origin, so since it's the origin, that's my y-intercept as well. It's symmetric with respect to the origin, so it's an odd function. If I plug in a negative x, I get out the opposite of tangent inverse x. Those lines, y equals negative pi half and y equals positive pi half, are horizontal asymptotes. Okay, those are the three main trig functions. We are going to just discuss those and work with those as far as looking at the graphs in a major way. But on the next page, we're going to kind of combine the other three, those remaining inverse circular functions. Tangent was y over x. Cotangent, though, cotangent theta is x over y. So instead of having y in the dominant position, now x is in the dominant position. Remember, cosine inverse was restricted from 0 to pi inclusive. Cotangent inverse is restricted from 0 to pi not inclusive. Secant is the reciprocal of cosine. So it is also going to be restricted by those cosine inverse restrictions, except remember that secant is undefined at pi half. So we're going to include 0 and pi, but we have to leave out pi half because secant is undefined there. What about cosecant? Well, cosecant is the reciprocal of sine, so it goes with those sine inverse restrictions, but cosecant is undefined at 0, so we have to leave it out. That's what these three graphs look like. We're going to go ahead and put the domain and range as well as the quadrants down in a chart so you have it all in one place. We're going to start with sine inverse. Sine inverse has a domain of -1 to 1 and an interval. Remember, we restrict sine inverse to quadrants 4 and 1. That's the interval from negative pi half to positive pi half inclusive. Now, this is sine inverse, it's y dominant, correct? Y over r is sine. What other functions are y dominant? Well, tangent is y over x. So tangent inverse is going to be related to the restrictions for sine inverse. Tangent inverse is also restricted to quadrants 4 and 1. But remember, instead of inclusive at those ends, it's open. So it doesn't include negative pi half or positive pi half. It includes everything in between. My tangent function value can be anything. So the domain is all real numbers. We have one more function, inverse function, that's restricted to quadrants 4 and 1. Sine inverse, tangent inverse, and then my reciprocal of sine inverse, cosecant inverse, is also restricted to quadrants -4 and 1. For cosecant, where's cosecant undefined? Well, it's undefined at 0. So I get to include negative pi half, go up to 0, but I got to leave it out. And then I include positive pi half. So that's what the range interval looks like for cosecant. My cosecant function values, remember the domain of sine is everything between -1 and 1. The domain for cosecant is going to be everything outside of that. All right, now let's look at cosine inverse. Cosine inverse also has a domain -1 to 1 because that's my cosine function values that work. It is restricted though to quadrants 1 and 2. Cosine is positive in quadrant 1, negative in quadrant 2. So that is from 0 to pi. Cosine is x over r. Cotangent is x over y. So it's going to have the same basic restriction as cosine inverse, restricted to quadrants 1, 2, except that it's not inclusive at those ends. It's 0 to pi, not inclusive. Just like tangent inverse, cotangent inverse compares the x to the y, so those domain values are all real numbers. And then I get to the reciprocal function of cosine, which is secant. So cosine inverse, the reciprocal is secant inverse. When I flip that domain, instead of everything between, I've got everything from the ends. It's restricted also to quadrants 1 and 2, except secant, if you look at your unit circles, secant is undefined there in the middle at pi half. So I'm going to go from 0 inclusive up to pi half, or pi half to pi inclusive as my interval for the range. All right, let's move on. Kind of keep this handy. This may help. Or it might help to kind of sketch a graph, whatever you need to do to remember what is restricted where for these inverse function values. Okay, moving on to example 3. We're going to find the inverse function values, and it says degree measured angles. So we're going to give our angles in degrees, not radians. It helps if you will identify the range of the function first. Identify the range of the inverse function first. So think about what two quadrants you're restricted to. Arctangent, tangent inverse, it's y dependent, y over x. So it's restricted to quadrants 4 and 1. If it's positive, then I know I have an angle that I'm looking for in quadrant 1. Well, what angle in quadrant 1 has a tangent value of square root 3? What is that angle theta? In quadrant 1, the angle theta with a tangent function value square root 3 is 60 degrees. Okay, what about cosecant inverse? Cosecant inverse. Cosecant is the reciprocal of sine, so we're still in quadrants 4 and 1. We've got a negative value, so we know we're looking for a negative degree measured angle in quadrant 1. So I'm looking for the angle whose cosecant value is negative square root 2. That is a negative 45 degree angle there in quadrant 4. I've been saying quadrant 1. I apologize to you. Cosecant function values are negative in quadrant 4. I was picturing it in my head and then I said it completely wrong. I'm over here in quadrants 1 and quadrants 4, but cosecant is negative down here in quadrant 4. So I'm looking for an angle in quadrant 4 with a cosecant function value of negative square root 2. Well, that's going to be the negative 45 degree angle down here in quadrant 4. Okay, arctangent 1. Arctangent is quadrants 4 and 1 again. Positive in quadrant 1. What is my tangent angle whose tangent function value is a positive 1 in quadrant 1? Well, it's 45 degrees. What is my angle theta whose secant inverse is 2? Secant inverse is 2. Well, secant is the reciprocal of cosine, so I know I'm looking at quadrants 1 and 2 this time. This is a positive secant value, so it's got to be in quadrant 1. What angle has a secant value of 2 in quadrant 1? Well, that's 60 degrees. All right, guys. Use this following statement to evaluate these inverse trig functions on a calculator. Now, we know if it's an exact value, we're thinking about special angles on our unit circle. If it's not an exact value, though, if it's not a special angle value, then we have to use our calculator. Secant inverse can be evaluated as cosine inverse of 1 over x. Cosecant inverse can be evaluated as sine inverse of 1 over x. So instead of using x, I use 1 over x if I'm having to use my inverse function button. I don't have an inverse function button for secant, so I can use cosine, but I do 1 over whatever I'm given as x. If I need cosecant, I use sine inverse, but I do 1 over whatever value I'm given of x. Now, cotangent inverse. We've got a little bit of an issue with cotangent inverse. Let's think about why that might be. If I think about where my trig function values are defined, remember that tangent inverse is negative in quadrant 4, positive in quadrant 1, while cotangent inverse is positive in quadrant 1, that matches, but it's negative over here in quadrant 2. Cotangent inverse is negative in quadrant 2, but tangent inverse is negative in quadrant 4. Now I can use my inverse function button for tangent inverse to evaluate cotangent inverse, but if I start out with a negative value of x, a negative inverse cotangent value, when I switch and use tangent inverse to evaluate it, it's going to return an angle in quadrant 4, and that's not what I'm looking for. If it's positive, I'm fine. They're both defined in quadrant 1 for positive values. But if it's negative, see, if I'm positive, I'm fine. No issues. But if it's a negative inverse value that I'm given, if I start with a negative x, I'm wanting an angle in quadrant 4. I'm wanting an angle in quadrant 2. I get an angle in quadrant 4. So I have to remember to rotate that thing around. If I add either pi or 180 degrees, depending on if I'm in degrees or radians, if I add it, it will move my angle from quadrant 4 to quadrant 2, because cotangent inverse is defined for negative values in quadrant 2. Tangent inverse is going to return an angle in quadrant 4. Okay, that's the only situation where I have to worry about it. Otherwise, what I get from my calculator is going to work. Now, we are going to, in general, give our answer in 4 decimal places. If I am using my calculator to approximate, I'm going to give an answer with 4 decimal places while I'm doing these notes, just so you know what we're looking for. I need to find y in radians, so make sure you're in radian mode in your calculator. That is super important. Secant inverse of -4. Well, I don't have a secant inverse button, but I do have cosine inverse. So I'm going to use cosine inverse. Take the reciprocal of the value. Take the reciprocal of this x I'm given. So that is a -1/4 instead of a -4. This is what I plug into my calculator, making sure I am in radian mode. And I get a radian angle value for theta of 1.8235 approximately. Now let's show you what that looks like on your calculator. Make sure you can see my calculator. Okay, so first I want to make sure that I'm in radian mode. I am not. I'm in degree mode. So I need to change that to radian mode. And then I'm going to say cosine inverse of a negative, make sure you use your negative button, not the minus, 1 divided by 4. Enter. There you go. Okay. Let's look at the next page of notes. Let's do it again. This time I'm asked to find arc cotangent in degrees, so switch to degree mode. We're finding arc cotangent of -0.2528. That's my cotangent function value. Here we go. Arc cotangent is restricted to quadrants 1 and 2. My negative cotangent, arc cotangent values are in quadrant 2. That's not what I'm going to get if I'm using tangent inverse, and I have to use tangent inverse. So tangent inverse of a -1 over 0.2528. That's what I have to plug into my calculator. Well, tangent inverse is restricted to quadrants 1 and 4, and it's negative in quadrant 4. So I'm going to have to move from quadrant 4 to quadrant 2. So I'm going to have to move my angle theta from quadrant 4. I get a negative value in quadrant 4. I'm in degrees. So I need to move it to quadrant 2 where cotangent inverse is defined for negative values. And I'm going to do that by adding 180 degrees. If I were in radians, I would add pi, but I'm in degrees, so I'm going to add 180 degrees. Okay, when I plug this into my calculator, I get out about a negative 75.8129 degrees. That is in quadrant 4. I need an cotangent value. That's going to have to be in quadrant 2. To get it there, I add 180 degrees. So the answer that I'm looking for is a positive 104.1871 degrees. That's the only situation where I have to do that rotation, only if I start with a negative arc cotangent or negative cotangent inverse. All the rest are going to be fine. They're going to stay where they're found. Okay, let's look at y in radians. Make sure you switch your mode again. Cosecant inverse of negative 3 means I'm going to be plugging in sine inverse of a negative 1 over 3. And then finally, I've got degree mode, arc cotangent. We're going to have to move it again. I do tangent inverse of negative 1 over 0.3541. I get out a negative, I can't see what I get out negative. Let me do this in my calculator. So clear, need to switch back to degree mode. And I'm going to do second function tangent of a negative 1 divided by 0.3541. All right, I get out a negative 70.5 something, and I'm going to add to that 180 degrees. So there's the angle that I need. So I get out a negative 70.5009. I have to add 180 degrees to that. The angle I'm looking for is 109.4991 degrees. Okay, be careful when you're using your calculator to evaluate the inverse cotangent of a negative quantity. This is what we've been talking about. To do this, make sure that you enter the inverse tangent of the reciprocal, which returns an angle in quadrant 4. And since inverse cotangent is negative in quadrant 2, you have to adjust your result by rotating it by adding 180 degrees or pi. Okay, remember that cotangent inverse of 0 is pi half. Let's work through example 5. It says to evaluate each expression without using a calculator. So we are not finding an approximate value or finding exact values, which means basically that we need to sketch our angle. So what I'm asked here is to find the cosine of some angle theta, and then I'm given information about angle theta. I'm asked to find the cosine of some angle theta, and theta is an angle whose sine function value is 2 over 3. Well, sine of theta is y over r. So when I'm given a sine function value of 2 over 3, I know y and I know r. All right, my sine function value is positive. I know that sine inverse is positive in quadrant 1, so there's my angle. Y is 2 and r is 3. I need to know x. Well, how do I find x? I use the Pythagorean theorem. So I have x squared plus y squared equals r squared, where y is 2 and r is 3. So x is going to be the square root of, that needs to be equal, 9 minus 4. And I know that x is positive because I'm in quadrant 1. So x is a positive square root 5. That's angle theta. And I need the cosine of theta. Well, cosine of theta is x over r. So cosine of this angle theta is square root 5 over 3. Let's look at B. My question here for B, what is the secant of some angle theta? And what I know about theta is that its cotangent function value is negative 15 over 8. So what is the secant of some angle theta? And I know about my angle theta that the cotangent inverse value, so the cotangent function value is a negative 15 over 8. Well, cotangent is negative over in quadrant 2. So I know that this is my angle theta with a negative 15, because cotangent is x over y, negative 15 over 8, and I need to find r. Again, I use x squared plus y squared equals r squared. So r is going to be the square root of, and r is always positive, r is going to be the square root of negative 15 squared plus 8 squared. R comes out to be, when I simplify all that, r comes out to be 17. Now, the secant of theta, secant is the reciprocal of cosine. Cosine is x over r, so secant is r over x. So secant of this angle theta that I've been given information about is a negative 17 over 15. Negative 17 over 15. That's kind of hard to see. Negative 17 over 15. All right, for C, I'm asked to find the sine of some angle theta, and then I'm given information about angle theta. I know that the tangent inverse function value, the tangent function value is 3 over 2. Tangent inverse is positive in quadrant 1, so my angle theta that I'm interested in is in quadrant 1. Tangent is y over x. Y over x. I need r. Using the Pythagorean theorem, I discover that r is square root 13. Sine of this angle right here is going to be y over r. And then I need to rationalize my denominator. So I've got 3 square root 13 over 13 as my sine value of that angle. And finally, D, I need a tangent function value of some angle theta. And I know this about theta. I know that my cosine function value is negative. Well, cosine is restricted to quadrants 1 and 2. And it's negative in quadrant 2, so this is my angle theta. I know that I have a negative 5 as x and 13 as r, and I need to solve for y. I'm going to use Pythagorean theorem to solve for y, and I get 12. Tangent of this angle, y over x, is a negative 12 fifths because my x value is negative. All right, remember you can always stop this. I'm going too quickly for you to be working this out on your own. Just stop the video, pause the video, work it out, and then come back. Okay, we've got a couple more examples to go through. I know this is a really, really long section. Sine difference. We're using a sine difference identity here. We're going to be finding function values using identities. We're doing a sine difference identity. If I look at this, what I basically have is sine of angle A. I've got information about an angle A, and I've got an information about an angle B. So I need to look and see what is going on with angle A and with angle B. Let me kind of divide up our space so that I know where my restrictions are. I've got angle A and I've got angle B. I've got our tangent value for angle A, it's positive, so angle A is in quadrant 1. I've got cosine value, our cosine value for angle B, it's also positive, so it's going to be in quadrant 1. For angle A, tangent is y over x, so that is going to be 4 over 3, and I'm looking for r. For B, cosine is 12 over 13. Cosine is x over r, so that is 12 and 13, and I'm looking for y. Using the Pythagorean theorem, I discovered that for angle A, r would be 5, and for angle B, y would be 5 as well. That just happened. That's just a coincidence. That is not something that you need to expect to happen every time. Now, I established that I'm going to need to use my sine difference identity. Sine difference identity. Sine of A minus B is equal to sine A cosine B minus cosine A sine B. Those are the values I plug in. Well, sine of angle A is 4 over 5. Cosine of angle B is 12 over 13. Cosine of angle A is 3 over 5. And sine of angle B is 5 over 13. When I do that arithmetic, I get 48/65 minus 15/65, which is 33/65. All right, the next one, we are looking at sine of 2 times the arc cotangent -5. So this is a double angle identity. This is, if this is A, this is sine of 2A. So I'm doing sine of 2A, and my double angle sine identity, if I look at my identity sheet, is 2 sine theta, or sine A. I started with A, let's do A. 2 sine A cosine A. 2 sine A cosine A. So I need to know the sine of A and the cosine of A, which means I need to sketch my angle. Arc cotangent is negative. It's negative in quadrant 2, so I'm over here. Cotangent is x over y, so I've got a -5 and 1, and I need to find r. When I work that out with Pythagorean theorem, I find out that r is square root 26. So sine of 2a, my double angle identity, sine identity, is 2 times the sine of a, which is 1 over square root 26, times the cosine of a, which is a -5 over square root 26. I'm not going to rationalize until the end because I don't want to cause more work for myself. So my numerator is 2 times -5, which is a -10. My denominator is 26, which reduces to -5/13. So for these, your first step is to identify which identity you need to use, and then you're going to find the missing values for your angles and simplify. For C, I've got a double angle tangent identity. My tangent double angle identity, if I look back at my identity sheet, my double angle tangent identity is 2 tangent A over 1 minus tangent squared A. So I've got 2 tangent theta over 1 minus tangent squared theta. I need to know my values for tangent. So I sketch my angle. Sine is positive. Sine is restricted to quadrants 4 and 1. It's positive in quadrant 1. Y over R. Y over R. I need to find x. I discover that x is square root 21. So I plug in my values. I get 4 over square root 21 in my numerator, 1 minus 4 over 21 in my denominator. Well, my denominator, if I do 1 is 21 over 21, my denominator becomes 17 over 21. And I'm going to treat this like a big division problem. So I'm going to multiply by the reciprocal of the denominator. So I've got 4 over square root 21 times 21 over 17. And then I'm going to need to rationalize that because I've got that square root 21 in the denominator. So what I end up with square root 21 times square root 21 is just 21. So that cancels out. I've got 4 square root 21 over 17 as tangent of that double angle. I'm not going to work you through all the steps on D. I'm going to tell you, you know what? We got cosine sum identity. Sketch both your angles A and B like we did in our first example. Plug the values into that cosine sum identity. And what you should end up with is this. All right, example 7. I warned you guys this was a super long section. Example 7. We're writing the trig expression as an algebraic expression in terms of u. I have cotangent of some angle And I have information about that angle. I know that the secant inverse value of this angle is u. Well, secant, let's say secant A is r over x because it's the reciprocal of cosine. And I'm told that that value is u, so that would be u over 1. So r is u and x is 1. That's right there. So we've got our angle theta right here. So if r is u and x is 1, what is y? We need to figure out what y is. X squared plus y squared equals r squared. So y is going to be the square root of r squared minus x squared. Well, r squared is u squared and x is 1. So x squared is 1. So y is square root of u squared minus 1. And I want to know the cotangent of this angle. Well, cotangent theta is x over y. X is 1. And y, we have discovered, is square root of u squared minus 1. I just need to rationalize that denominator. So I get square root of u squared minus 1 over u squared minus 1. Using that same angle. Oh no, this is a different setup. This is a different setup. Let's switch gears. I'm sorry. We've got sine of 2 theta. Sine of 2 theta. Double angle sine identity. Well, I know that my double angle sine identity, if I look at my identity sheet, my double angle sine identity is 2 sine theta cosine theta. So I need to know both of those things. And theta, I know that my cosine inverse function of theta is u. So over here, if this is theta, because it's positive, it's in quadrant 1. Cosine inverse value is u. Cosine is x over r. So that's going to be u and 1. Notice that reverse position. So I need to recalculate y. Y is still going to be r squared of r squared minus x squared. In this case, r is 1 and x is u. So 1 minus u squared. Square root of 1 minus u squared. That's my value for y. Square root of 1 minus u squared. So I've got x, y, and r. Sine of the double angle is 2 times sine is y over r. Cosine is x over r. Look at that, I didn't need that denominator of 1. We've got 2u times the square root of 1 minus u squared. The important thing to remember about these is that when I'm given an inverse function value inside and something else on the outside, this is just information about the angle, and I am trying to find the angle. Our very last example, example 8, the very last example in this set of guided notes is basically calculator math. You've got a shot putter putting the shot, and he wants his optimal distance. So if you get your optimal distance, you don't want to go too far up because then it's going to come down. You don't want to go too far out because it'll fall flat. You want that perfect arc there. And the formula to get that optimal distance is arc sine of square root of v squared, where v is my velocity, over 2v squared plus 64h, where h is the height of the shot, so the height of where the shot starts. Suppose that a shot putter can consistently throw the steel ball with a height of 7.5 feet, so starting at that height at 7.5 feet, and a velocity of 50 feet per second. What angle should he release the ball to maximize that distance? This is just calculator math. When you plug it into your calculator, make sure you're in degree mode. You get an angle of 42 degrees. Now, that radical, what that should look like, is going to end up being 2,500 over 5,000 plus 480 if I plug in my values for h and v. And then, of course, I'm finding arc sine or sine inverse of that.